So now that we know that the valence electrons in atoms are the outside atoms, these are the ones that participate in bonding, let's look at covalent molecules bonding in terms of how we draw what's happening with the electrons. We are going to focus on covalent molecules. Recall that a covalent molecule is made up of nonmetals only, so we are going to be focusing over here on the right-hand side of the periodic table. So we can pretty much go ahead and get rid of the left-hand side. And we're going to be looking at how these atoms interact with each other to form molecules. Let's start with very simple things. And of course, I got rid of my hydrogen. Let's put our hydrogen right here by helium. Remember that he's atomic number 1. Hydrogen has 1 electron total. It is a valence electron. When we know that the natural state of hydrogen is diatomic, which means he wants to combine with other hydrogen atoms to form a hydrogen molecule. And so we can envision that happening if the two atoms get close enough to share these 2 electrons. These 2 electrons are shared between the 2 nuclei. Remember that each hydrogen has a proton in its nucleus. The most abundant isotope of hydrogen is hydrogen 1, which only has 1 proton. It doesn't have any neutrons. Remember that the protons are positively charged, and so the 2 plus centers of these atoms are being attracted to the 2 electrons being shared. That forms a bond between the hydrogens. I can redraw this with a dash joining the hydrogens. This dash represents 2 electrons being shared. This dash represents what we call a single bond. So this is how we can represent the structure of hydrogen. Let's try another example. Let's look at fluorine. Fluorine is over here in group 7A, so it has 7 valence electrons. We also know that fluorine naturally and normally wants to be diatomic, or is diatomic. And so let me draw another fluorine atom with its 7 valence electrons. Now we could draw the dots such that the lone dot, the individual dot, ended up on any of the 4 sides. I have purposely drawn it in this position so that you can see that if these 2 atoms get close enough together, they can share this pair of electrons, each of them bringing 1 to the mix. And this pair of electrons being shared then is a single bond between the fluorines. I can rewrite it as a dash between the fluorines, but I also want to include the other valence electrons of fluorine because they are important in the structure of it, as we'll see as we move on through this material. We've got some vocabulary here. Again, this pair of electrons being shared, this is 2 electrons, this is a single bond. This pair of electrons that is not being shared in any bond is called a lone pair of electrons. We also can call these a non-bonding pair of electrons. And you'll notice that it is a pair of electrons. When I am finished with the Lewis structure, this is called the Lewis structure of this molecule, the molecule F2, all of the electrons are in pairs. There's another lone pair, another lone pair, a lone pair, and a lone pair. And then my bond is also a pair of electrons. Now, we can end up with an odd number of electrons. These are called free radicals, and we're not covering them in this section. So all of your electrons will end up in pairs at this point in the game. Let's continue on and look at another example. Let's look at oxygen. Oxygen is in group 6A, so oxygen has 6 valence electrons. We draw them around the single oxygen atom, singly and then in pairs. So I have represented the 6 valence electrons of oxygen. We also know that oxygen is also a diatomic element, and so it wants to form a molecule with another oxygen atom. Each oxygen atom seeks out another oxygen atom in order to form a molecule. And so we can envision that if these 2 atoms get close enough, they can share these individual electrons in a bond. You'll notice that I'm still drawing the lone pairs that didn't participate in the bond. I can redraw this with dashes. You'll notice that the dashes connect the two oxygens, and what we've represented here is the bonding scenario in an oxygen molecule. These two pairs of electrons, or 4 electrons total, are called a double bond. We still have some lone pairs or non-bonding electrons on the oxygens. We've got another lone pair there, another lone pair there, and the 4th lone pair there. All right, let me redraw our fluorine to point out what's going on here. If we look at the Lewis structures of both oxygen and fluorine, what we see happening is that each atom ends up with 8 electrons surrounding it if we count the pairs that are shared in bonds. So the left oxygen has 8 electrons, 2, 4, 6, 8, and the right oxygen has 8 electrons, 2, 4, 6, 8. We'll always be counting in twos. We'll always have the electrons in pairs. If we look at what happened with the fluorine, the left fluorine has 2, 4, 6, 8. The right fluorine has 2, 4, 6, 8. So we see 8 electrons surrounding each atom in the finished Lewis structure. This is called the octet rule. We've been hinting at this all along, if not outright saying it, because there is something particularly stable about having 8 electrons in your valence shell. 8 electrons in the valence shell is the normal electron configuration for each of the noble gases except hydrogen. Hydrogen only has 2 electrons in its valence shell. The remaining noble gases, starting with neon on down, have 8 electrons in their valence shells, and this makes them particularly stable. This makes them particularly non-reactive, although some of the heavier ones we do see reactions with those. And so what we find is that the remaining nonmetals tend to try to strive to have 8 in their valence shell. We also saw these with the ions. The ions that form of the nonmetals to combine with metal cations to form an ionic compound also want 8 in their valence shell, and they actually take electrons away from metals. Here they're not taking electrons away from anyone, they're sharing them. Covalent molecules share electrons to form bonds, and therefore we count the shared electrons with each atom to get to 8, which is the octet rule. The only exception to the octet rule is hydrogen. Hydrogen does not want 8, hydrogen wants 2. Hydrogen wants 2 because he wants to look like helium, who has 2 electrons in his valence shell. And so the exception to the octet rule is hydrogen. There are a few other exceptions that we'll find and talk about as we move on, but right now this is the big one. So these are the basics of drawing Lewis structures. Let's do one more before we wrap it up, just to kind of complete this trend. We know that nitrogen is naturally and normally diatomic, and so let's draw what nitrogen would look like in terms of his Lewis structure. Nitrogen has 5 electrons. I've covered it up, but he's in group 5A. 5 valence electrons, 5 dots. A second nitrogen would also have 5 valence electrons, 5 dots. And we can kind of envision that if we scooch them together, they get close enough, they can share each of their odd electrons with the other nitrogen. And let me draw them closer together. I'll go ahead and draw these 3 pairs of electrons as dashes. I will continue to draw the lone pairs. I'm leaving them on the top, but I also could have put the lone pair off to the side or below the nitrogen. That part doesn't matter. And so I have here the Lewis structure for nitrogen, N2. I see a lone pair on each nitrogen, and here I see a triple bond. A triple bond contains 3 pairs of electrons, or 6 electrons total, and for us this is as high as it goes. We will not see any quadruple bonds in this course. Things get fancy whenever we get to heavier and heavier elements, and so sometimes we sort of see these, but that's for a later course. At this point, triple bonds are as high as they go. So this is the basics of Lewis structures, essentially taking the atoms with its valence electrons, the dot symbol that we learned about in a previous video, and pushing it closer to another atom in order to form the bonds.